Hey there, this is the first video for Chapter 7. We won't be having an exam for Chapters 7 or 9, but there is a combined quiz for those chapters, and their content will be included in the cumulative final exam. This first section really sets up the work you'll be doing in the next 3 sections of this chapter, so there aren't a lot of problems per se for this section, just terminology and understanding of concepts. I know this is a pretty long one, just hang in there with me and make sure you understand the terminology and can follow your lecture notes. You're not going to need your calculator or any tables or anything like that for this one. Just your lecture notes, paper, pen for notes. Okay, let's get started. Welcome to the lecture video for Chapter 7, Section 1, Introduction to Hypothesis Testing. Here's what we're going to cover. We're going to get a good foundational understanding of hypothesis tests as they apply to statistics. We're going to learn how to state a null hypothesis and an alternative hypothesis. We'll learn how to identify type 1 and type 2 errors and interpret the level of significance, and how to know what type of statistical test to use to find a p-value, a left-tailed, right-tailed, or two-tailed test. We're going to talk about how to make and interpret a decision based on the results of a statistical test, and how to write a claim for a hypothesis test. Here we go. So far in our study of inferential statistics, we've worked on creating confidence intervals for 2 types of population parameters. We used an x-bar and a margin of error to create a confidence interval for mu, and p-hat and a margin of error to create a confidence interval around the population proportion, p. We're going to introduce a new topic today. We're going to talk about hypothesis tests. A hypothesis test is a process that uses sample statistics to test a claim about the value of a population parameter. The goal of a hypothesis test is to either reject or fail to reject the claim. Look at this example. Consider a manufacturer that advertises its new hybrid car has a mean gas mileage of 50 miles per gallon. If you suspect that the mean mileage is not 50 miles per gallon, how could you show that the advertisement is false? The claim is that the car has a mean gas mileage of 50 miles per gallon. We're going to learn how to write hypotheses to test that claim. First, we need some vocabulary. The first term is a null hypothesis. Its notation is H sub 0, or H naught, and it is a statistical hypothesis that contains a statement of equality, like less than or equal to, equals, or greater than or equal to. The next term is alternative hypothesis, or H sub A. It is the complement of the null hypothesis. It is a statement that must be true if H naught is false, and it contains statements that are strictly inequalities, like greater than, not equal to, or less than. So if we take the example we just had about the hybrid car that has a mean gas mileage of 50 miles per hour per gallon, we might set up the following null and alternative hypotheses. We would say the null hypothesis, or H sub 0, or H naught, is that the mean, or mu, equals 50. You see how this is a statement of equality? We're using equals. This came from the original claim, a mean gas mileage of 50 miles per gallon. Then we would need to come up with a complement of that in an inequality. Well, the opposite or complement of equals is not equal to. So we would write H sub A is mu is not equal to 50. We want to test the original claim. And you probably noticed that we used mu in this instance, since the original claim was about the mean gas mileage. But these hypothesis statements can be made about any population parameters: mu, sigma, or population standard deviation, sigma squared, or population variance, or p, or population proportion. Let's talk about a few points about these hypothesis statements. First of all, the statements are about a population parameter, like we just said. Next, one of them, meaning either the null hypothesis or the alternative hypothesis, is going to represent the claim, and the other is going to represent its complement. Thus, when one of the hypotheses is false, the other must be true. So we have to word them in a way, mathematically, that makes one of them true. Also, you may have realized this in an earlier point, either one of the hypotheses The null hypothesis or the alternative hypothesis may represent the original claim. So we don't necessarily write the null hypothesis first. We may be writing the alternative hypothesis first because it describes the claim. Let's look more at that. Remember, we have strict rules about what sort of signs to use for each. We have to use some sort of equality sign for the null hypothesis. Less than or equal to, equals, or greater than or equal to. And we have to use strictly inequality signs for the alternative hypothesis. Less than, not equal to, or greater than. So look at this first example. If the original claim had been about something greater than something, we would have written the alternative hypothesis first, and then written its complement as the null hypothesis, with less than or equal to after that. Think about what that means. Greater than is everything above a number, not including the number. So the complement to that, or opposite, would include the number and everything below the number. So the complement to greater than is less than or equal to. Same goes for these others. And regardless of which direction you go with these signs, you always assume mu equals k and examine the sampling distribution based on that assumption. Here's a breakdown of the wording you might see and what symbols you might use for each one. I'm not going to read these to you, but I'll leave it on the screen for a moment in case you want to pause and write these down or get a screenshot of this table. This kind of specific information helps some people, so I want you to have it in case it does. Okay, so let's do a few examples. Write each claim as a mathematical sentence, state the null and alternative hypothesis, and identify which represents the claim. A school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. Okay, so they've given us some information in the way they stated it. To translate something into a mathematical sentence, we look for clue words. And one of those words is the word is, which in math means equals. So they've told us the equality symbol we're looking for in the null hypothesis is the equal sign. What else? They've also told us it's about proportion. So do you remember which population parameter that relates to? If you said P, you're right. So I think we can write at least our null hypothesis now. Let's do that. So H naught is P equals, and then we put the percentage into decimal form, 0.61. And we identify the fact that this is our claim. Good so far. Now we need to figure out our alternative hypothesis. If the null hypothesis used equals, we need to use its complement, or not equal to. So we need to simply say H sub A is P is not equal to 0.61. Good job. Let's try another. A car dealership announces that the mean time for an oil change is less than 15 minutes. Think about what our sign needs to be and whether it's an equality or inequality, and which hypothesis statement that means it goes with. I'll give you just a moment to think about that. Because the claim says less than, not less than or equal to, we're dealing with strictly an inequality. So our claim needs to go in the alternative hypothesis. And we're dealing with mean time, so that means mu. So H sub A is mu is less than 15 minutes, and that is our claim. Now we need to figure out what to put for our null hypothesis. And remember, we need an equality statement that is the complement to less than. That would be greater than or equal to. So H naught would be mu is greater than or equal to 15 minutes. Great work. Okay, let's do another. A company advertises that the mean life of its furnaces is more than 18 years. Think about which population parameter we're working with and what sign, and whether it's an equality or inequality. Pause the video and do this. Well, the claim states more than 18 years, so it's an inequality, which means we're doing the alternative hypothesis first and using greater than. And we're talking about the mean, so it'll be mu. So H sub A is mu is greater than 18 years, and this is the claim. Then we figure out that the complement to that statement is that H naught is mu is less than or equal to 18 years. Nicely done. Our goal in a hypothesis test is to either reject or fail to reject the original claim. So to begin the hypothesis test, we need to assume that the null hypothesis is true. But since our decision is based off of a sample, there's always the possibility that we could get it wrong. The only way to be absolutely sure would be to test the entire population, and that is rarely feasible. So sometimes we're going to have to accept that there will be errors. So let's look at the type of errors that could be made. A type 1 error occurs if the null hypothesis is rejected when it's true. This means the equality statement made in the null hypothesis is a true statement and we rejected it. If we rejected it, a type 1 error has occurred. Okay, a type 2 error occurs when the null hypothesis is not rejected when it's false. This means that the equality statement made in the null hypothesis was false, not true, and we failed to reject it. We missed that it should have been rejected if we failed to reject it. That's a type 2 error. Let's look at a real-life example of this. The USDA limit for salmonella contamination for ground beef is 7.5%. A meat inspector reports that the ground beef produced at a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 or type 2 error occur? Which error is more serious? Let's look at how we would set this up as a hypothesis test. Because the USDA inspector's claim said the company exceeded a limit, that means greater than, which means the claim is going in which hypothesis statement? That's right, the alternative hypothesis. So we say H sub A is P, because this is a proportion question, is greater than the amount they gave us in decimal form, 0.075. That is the claim. Then we write its complement as the null hypothesis. H naught is P is less than or equal to 0.075. Now, just to keep things clear, the safest thing to do in this case is to reject the null hypothesis, because that would agree with the inspector's claim and keep contaminated meat off the shelves, if they are in fact contaminated. But for the purposes of this hypothesis testing, we actually would assume that the null hypothesis is true. If we do that, which type of error are we committing? And remember, this is the type of situation real-life companies have to weigh on a daily basis. Let's read on. A type 1 error is rejecting H naught when it is true. The actual proportion of contaminated ground beef is less than or equal to 0.075, but you reject H naught. So this would be if there was actually less than the stated amount of contaminated meat, but we rejected that stated amount and insisted that there was more contaminated meat. A type 2 error is failing to reject H naught when it is false. The actual proportion of contaminated ground beef is greater than 0.075, but you did not reject H naught. This is the error we would be committing if we decided not to take the inspector's advice. Let's look at the repercussions and which would be more dangerous. With a type 1 error, where we believe there is more contaminated meat than has actually been told to us, you might create a health scare and hurt the sales of ground beef producers who are actually meeting the USDA limits. This could have serious economic consequences. But with a type 2 error, where you ignore the inspector's warning and fail to reject the null hypothesis, you could be allowing ground beef that exceeded the USDA contamination limit to be sold to customers, which could cause a serious health situation. A type 2 error is more serious because it could result in sickness or even death. So we know we should reject a hypothesis when the results of our sample are unusual, when the probability of those results occurring is less than a 5% chance. Sometimes other levels of probability are used. You might see it at the 10% or 5% or 1% level. When the probability of our results happening is less than those limits, we have the credibility or evidence to reject a hypothesis because the results are unusual. Sometimes results are odd, though. How do we counteract accidentally rejecting something that is true just because a sample is a little unusual? To counteract those types of errors, specifically a type 1 error, which if you'll remember was to reject a null hypothesis that was true, we use what's called a level of significance. It is the maximum allowable probability of making a type 1 error. It is denoted by the lowercase Greek letter alpha. By setting the level of significance at a very small value, you're saying you want the probability of rejecting a true null hypothesis to be small. The levels that are most often used are 10%, 5%, and 1%, represented here in decimal form. The probability of a type 2 error happening is denoted by the lowercase Greek letter beta. After stating the null and alternative hypothesis and specifying the level of significance, the next step is for a random sample to be taken from the population. At that time, sample statistics like x-bar, p-hat, s or s squared, also known as test statistics, which correspond to the parameters of the null hypothesis like mu, p, sigma, or sigma squared, are calculated. With the assumption that the null hypothesis is true, the test statistic is then converted to a standardized test statistic such as z, t, or chi-squared. Then the standardized test statistic is used in making a decision about the null hypothesis. This table shows the relationships between the different variables you've been working with, and some you'll learn soon. And one thing to note is that a way to reject the null hypothesis is to determine whether the probability of obtaining the standardized test statistic is less than the level of significance. A p-value or probability value is the probability, if the null hypothesis is true, of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. The p-value of a hypothesis test depends on the nature of the test. There are three types of hypothesis tests: left-tailed, right-tailed, and two-tailed tests. The type of test depends on the region of the sampling distribution that favors a rejection of H0. This region is indicated by the alternative hypothesis. Since alternative hypothesis statements are strictly inequality symbols, that means the statement points to the area of the standard normal curve or the t-distribution that we should be testing. Let's look at different types of tests. Let's look at the right-tailed test first. The alternative hypothesis H sub A reads mu is greater than k. So if you look at the graph, P is the area to the right of the standardized statistic. That's called a right-tailed statistic. Makes sense, right? The area filled in is on the right. Now the left-tailed statistic. H sub A reads mu is less than k, and P is the area to the left of the negative standardized test statistic. I bet you can guess what's going on with the two-tailed test. The two-tailed test is used for the inequality symbol. Each tail has an area of half of P, 1/2 to the left of the negative standardized test statistic, and 1/2 to the right of the positive standardized test statistic. Okay, so this is always done with the alternative hypothesis because it will always have strictly inequality symbols. We should be able to tell from any set of hypothesis statements what the graph should look like. Let's look at our examples from before and determine how they would be graphed. For each claim, state H0 and H sub A in words and symbols, then determine whether the hypothesis test is left-tailed, right-tailed, or two-tailed test. Sketch a normal sampling distribution and shade the area for p-value. Number 1. A school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. So before we found that the null hypothesis was equals, and the alternative hypothesis was not equal to. So that means we're going to do which one of those three tests: left-tailed, right-tailed, or two-tailed test. If you said two-tailed, you are paying attention. Thank you. The alternative hypothesis drives the nature of this test, and its inequality symbol, not equal to, said this would need to be a two-tailed hypothesis test. So the shaded area representing the area of the p-value would lie to the left and right of the negative and positive standardized test statistic. Okay, next one. Number 2, a car dealership announces that the mean time for an oil change is less than 15 minutes. For this one, we started with the alternative hypothesis because that aligned with the claim, which was less than 15 minutes. And the null hypothesis was greater than or equal to 15 minutes. So if less than 15 minutes is our H sub A, which test are we dealing with? That would be left-tailed, because it's pointing to the left, less than. The area shaded for the p-value would be to the left of the negative standardized test statistic. Last one, number 3. A company advertises that the mean life of its furnaces is more than 18 years. Which type of test is this one? We had to start with the alternative hypothesis for this one too, because it's dealing with more than 18 years, so greater than 18 years. That tells me we're dealing with a right-tailed hypothesis test, and the area of the graph shaded for the p-value is to the right of the standardized test statistic. Alright, we're skipping over some steps in actual testing because we'll talk about that more in later sections. But now we're going to talk about after the testing happens and how to make a decision based on p-value. Here's how that works. You compare the p-value with alpha, or the level of significance that we talked about a moment ago. If the p-value is less than or equal to the level of significance specified, then we reject the H0 or null hypothesis. That means that the p-value is unusual, so much so that it is within the bounds of our very low level of significance we talked about. So it causes us to reject the null hypothesis. If the p-value is higher than alpha, then we fail to reject the null hypothesis. Remember, we're not accepting anything, we're just rejecting or failing to reject. In this case, if the results are not within the unusual bounds or the level of significance, we're saying we're failing to reject the null hypothesis. So we're not given an alpha value on these next examples, but we're going to take a few of the problems we've been working with throughout this lesson and talk about how we'd word rejecting and failing to reject the claims. Number 1, the claim is that a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. We said the null hypothesis was equal to 61%. Here's how you would word this. If you reject the null hypothesis, or H0, you should conclude there is enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. And if you fail to reject H0, you should conclude there is not enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. Okay, let's look at the next one. Number 2, a car dealership announces that the mean time for an oil change is less than 15 minutes. This is a little trickier because the null hypothesis did not contain the claim. The claim is represented by H sub A, which is that a car dealership announces that the mean time for an oil change is less than 15 minutes. The null hypothesis is the mean time for an oil change is greater than or equal to 15 minutes. So on this one, you have to think in terms of what the null hypothesis says, not what the original claim says. The null hypothesis is saying the mean is greater than or equal to. The way to reject H0 would be to conclude there is enough evidence to support the dealership's claim that the mean time for an oil change is less than 15 minutes. The second part, if you fail to reject H0, you should conclude there is not enough evidence to support the dealership's claim that the mean time for an oil change is less than 15 minutes. So here's the rundown on the steps for hypothesis testing. These steps are in your lecture notes, so make sure you keep them handy or mark them somehow so you can find them easily. Here goes. First, state the claim mathematically and verbally. Identify the null and alternative hypotheses. Then you want to make sure you know what the level of significance is that you're testing at, the alpha value, 10%, 5%, or 1%. Once you've got those statements, you have enough to figure out at least a sketch of the graph for standardized sampling distribution. And that is based off the assumption that the null hypothesis is true. The nature of the test is going to depend on how you wrote your alternative hypothesis. Next, calculate the test statistic and its standardized value and add that to your sketch. After that, you find the p-value. Then use the following decision rule. Is the p-value less than or equal to the level of significance? If it is, you need to reject the null hypothesis. If it's not, you fail to reject the null hypothesis. And lastly, write a statement to interpret the decision in the context of the original claim. Okay, good job. That was just an intro to this chapter and this topic. We're going to get into actual problems in the next sections. Good job. I'll talk to you in the next video.